This talk is a crash course in infrared missions. NASA has many space-based telescopes, but really only 4 have gotten the special name of Great Observatories. There's the Compton Gamma Ray Observatory, which is no longer flying, the Chandra X-ray Observatory, which is flying, the Hubble Space Telescope in the optical, which is flying, and the Spitzer Space Telescope, which is no longer flying, but observed in the infrared. And that is the infrared mission that we're going to be talking about in part today. Why do we need to go to space to do infrared astronomy, or for that matter, gamma ray, X-ray, or UV astronomy? Well, the atmosphere absorbs these kinds of wavelengths of light. Here we've got a cartoon transmission as a function of wavelength. If you are a gamma ray astronomer, an X-ray astronomer, or an ultraviolet astronomer, you have no choice. You have to go to space because those wavelengths of light don't make it down to the ground unscathed. If you're an optical astronomer, you can do astronomy from the ground, no problem. If you pick your wavelength just right and you get to a very, very high, very dry mountaintop, you can do some kinds of infrared astronomy, but it is hard to do. For the longer wavelengths of infrared astronomy, you have to go to space. You have no choice. And for radio astronomy, you can do radio astronomy from the ground. You do not have to go to space. So that's one of the big reasons is you have to go to space to do it, because the light doesn't make it down to the ground. For infrared astronomy in particular, the other big reason is that space is cold. If you're trying to do infrared astronomy from a mountaintop, your telescope is the same temperature as the temperature of the air around your telescope. And the best analogy I've heard to describe this is, imagine trying to do optical astronomy from a telescope that's made out of those fluorescent tubes of light, the fluorescent light tubes. Because your telescope in the infrared is glowing. If your telescope is warm, then your telescope is glowing in the infrared. So by getting up into space, your telescope can cool off. And then it becomes a lot easier to observe in the infrared because your telescope is not warm. Your telescope is cold. So those are the 2 big reasons why we need to go to space to do infrared astronomy. We've had a small fleet of infrared telescopes. There's little icons there that and the dates that those missions flew. There was IRAS in the 80s, was the first all-sky infrared survey. There's ISO and IRTS, both in 1995. There's MSX, which was a survey of the Galactic Plane in 1996. And then we've got Spitzer, which was launched in 2003 and was decommissioned in 2020. There's Akari, which flew between 2006 and 2011. There's WISE, which was launched in 2009 and is still operating. Then there's Herschel, which operated between 2009 and 2013. The 2 telescopes that I'm going to focus mostly on in the rest of this talk are Spitzer and WISE, but Herschel gets some time because I use those data a lot. And Akari also often gets used. I'm not going to talk too much about Akari here, but I mention it because it gets used a lot in a lot of the NITARP projects. So where do these spacecraft launch from? So WISE, and for that matter IRAS, launched from Vandenberg. And you won't be surprised, therefore, to learn that they have similar orbits because they launch from the same place. Spitzer launched from Canaveral, Cape Canaveral in Florida. Herschel launched from French Guiana, so you can know right away that those things probably have much different orbits than WISE and IRAS do. This is what WISE's launch looked like. WISE is the Wide Field Infrared Survey Explorer. It's a NASA-funded mission. It was launched, as I said, from Vandenberg in 2009. So both IRAS and WISE have these polar orbits. So this video here, at a representation of Earth at the center. What's going on is it's orbiting Earth, and with every orbit, the orbit precesses a little bit. And so with one orbit, it takes a series of exposures, and the next orbit is a very little bit offset. And over many orbits, you're going to cover the whole sky. The poles, the north and south ecliptic poles, get covered every orbit. Stuff on the equator gets covered several times, but then only every 6 months do you hit that same chunk of sky. You come back and hit that same chunk of sky again. So these polar orbits, each orbit takes about 90 minutes. So it's orbiting relatively close to the Earth. And when you have this kind of an orbit, the presence of the Moon and the Earth both matter a lot. It is orbiting within much of the radiation belts of Earth, so that matters. This kind of orbit, however, is called a sun-synchronous polar orbit. It is orbiting at basically the sunrise-sunset terminator, and it precesses at about the same rate as the sunrise-sunset terminator. That's why it's called sun-synchronous. And it's a polar orbit because it hits the poles on every orbit. This is what the IRAS spacecraft looked like. It had a beryllium telescope that was cooled to about 4 Kelvin with helium. So the telescope was entirely inside this cryogen bath. So when they went to go design Spitzer, because IRAS had worked, they thought, okay, we're going to do the same thing. We're just going to make it bigger. Well, stuff happened. Budgets got cut, but some clever engineers figured out a way to make the telescope the same size, but have the telescope not inside the cryogen, have the cryogen external to the telescope, but exhaust past the telescope, and that's how it stays cool. It also passively cools with some really, really clever thermodynamics. That's a whole separate lecture. The thermodynamics of Spitzer is really cool. But you can see here that the telescope is physically much smaller. The amount of cryogen is much smaller, but the telescope is the same size. So when you do that, you have, because you don't have to cool down the whole telescope to test it, it becomes easier to test it. And because the whole thing is smaller, you don't have as big a rocket, so it's become cheaper. Huge savings of money for the same telescope aperture. So that was able to save Spitzer when it was on under several different budget cuts. So that's what Spitzer looked like when they were assembling it. You can see it's not very big. You can see the people. The telescope lives in here. This is where the instruments are. This is where the cryogen was. This is what the engineers call the spacecraft. It's all the electronics, communications, all of that. Here's solar panels. This side is painted silver so that any little bit of sunlight that makes it past the solar panels gets reflected away there. That side is painted black so that it passively cools by radiating off into space any excess heat there. Here is what the WISE spacecraft looks like. Again, really, really amazing thermodynamics. Again, whole separate lecture. It has to deal with a much different orbit, and so it has to deal with a much different thermodynamic environment. Again, really, really clever engineering that I don't have time to go into here, but it has, instead of liquid helium on board, it had solid hydrogen on board. It was cooled to below 12 Kelvin when it had the cryogen on board. This is what it looks like inside. Now, just to compare the mirror sizes to scale, there's the IRAS mirror, which was a 57 centimeter beryllium mirror. And then the WISE mirror was a 40 centimeter aluminum mirror. That's me. And that's my son in 2013. He would want me to point out that in 2023, he's now taller than I am. But those are us to scale with those mirrors. So we could hug WISE without too much problem. Even when the mirror is inside the spacecraft, we could hug WISE without too much problem. There's Spitzer. Spitzer is an 85 centimeter beryllium telescope. So Spitzer is much bigger than the others. We'd have a hard time hugging Spitzer. Herschel, in contrast, is a monster. Herschel is 3.5 meters. Okay, and it's silicon carbide mirror. It's enormous. So it's not surprising that the size of the telescope is related to the wavelengths it observes. There's the relationship down there for those of you who are interested in pursuing that, beyond what I'm going to cover right here, right now. Just for context, though, that's JWST. So there's the Spitzer primary mirror, 85 centimeters to scale. There's the Hubble primary mirror, and there's the JWST primary mirror. So JWST is a monster, too. Okay, orbits. I have a whole series of snapshots here, which are really cool. They're from an application called Eyes on the Solar System that JPL has. You can run it independently or within a web browser. If you have not played with this yet, you really should. It's very, very cool. So this is Hubble. It is in low Earth orbit. This is a really, really good orbit if you need to service the spacecraft, because when we had the shuttle operating, the shuttle could get there and change things out, which was one of the whole purposes of putting Hubble in this orbit. That's a really, really good thing. But you can see the Earth looms large from its perspective. So this is a bad orbit in context of not trying to look at the Earth, right? So a significant fraction of Hubble's life is spent simply trying not to look at the Earth and the Moon, because it's right there. It's huge. The Earth looms large. But when you think of spacecraft in orbit around Earth, you probably are imagining something like this, right? It's right close to the Earth. You can see that there's all sorts of orbits in there. There are lots and lots of satellites in low Earth orbit, and these are just a few of the satellites that are up there. So now we're going to zoom out a little bit. That's Hubble's orbit in there. We're starting to see more and more and more spacecraft in there, but where are the other telescopes? That's Chandra. Chandra has a long elliptical orbit around the Earth. It actually takes it about a third of the way to the moon and back. We're going to zoom out even further. I don't know if you can see them, but there's two spacecraft there marked Van Allen Probe A and Probe B. Those two Van Allen satellites were specifically launched to study the Van Allen belts. Van Allen belts are these charged particles that are trapped in our magnetic fields. They're really, really cool. They were discovered in the 50s as soon as we started launching spacecraft. And it turns out that they are really, really hard on spacecraft. Now, think about this. The Chandra X-ray telescope is designed to focus X-rays. Have you thought about that? I mean, you're used to thinking of X-rays as going through something. Like you take an X-ray at the dentist office or of a broken bone, and the X-rays go through your hand or your jaw. How are you going to focus X-rays when the X-rays are going to go through a mirror? Well, the way that you do that is you have cylindrical mirrors where the X-rays sort of glance off of the surface of the mirror to focus. Well, those kinds of energies, you're going to focus particles too. So with the kind of orbit that Chandra has, every so often it gets carried through some of these radiation belts and through something called the South Atlantic anomaly, which is part of the Van Allen belts, which is a concentration of charged particles above, the South Atlantic right above the South Atlantic on Earth. And when it goes through the South Atlantic anomaly, it focuses all of those charged particles on the detectors in Chandra. That is not good. The South Atlantic anomaly can and has damaged spacecraft, and it's really hard on Chandra every time it goes through the South Atlantic anomaly. So those belts really beat up spacecraft. We're going to zoom out even further. So in September 2019, there's the Sun, Earth, Kepler, and Spitzer. Look at that. There's Mercury, Venus. Here's right after launch in 2005. There's the Earth and there's Spitzer. Because what happened is we launched Spitzer and we kicked it out with enough energy to leave the Earth-Moon system and just start trailing behind it. This is 5 years after launch. This is the end of the nominal mission and the end of the cryo, when the cryogen ran out on Spitzer. Spitzer was a decent fraction away from Earth. By September 2019, there's the Earth and another telescope called Kepler in the same kind of orbit, and there's Spitzer back here. Mercury and Venus for scale. In January 2020, which is the end of the mission, there's the Sun, Mercury, Mars, Venus, Earth, and Spitzer. Look how far away Spitzer is. Spitzer is a long way away from Earth at that point. Really a long way away. So this orbit is really, really good for Spitzer because we didn't have to worry quite so much about spending time trying really hard not to look at the moon or the Earth. So we spent almost all of our time observing the skies, which is really good. We spent almost all of our time doing science. That's awesome. We did not have to worry about the Earth radiation belts, so we didn't have to worry about damage to the detectors or the electronics. The flip side of that, though, is that sometimes we saw flares from the sun that the Earth didn't even know were there. So, because we didn't have the Earth's magnetic field to protect us. So, there is that. We did have a much better thermal environment, though, because the Earth-Moon system is actually quite warm. So by getting away from the Earth-Moon system, we could passively cool off really, really efficiently. So we could just, without having a whole bunch of cryogen on board, even just passive cooling will, allowed us to cool down quite a bit. So that's a really awesome orbit. So connecting the dots here, the Earth trailing orbit, plus the fact that we could passively cool efficiently, plus having, I didn't mention this, but Spitzer has no moving parts. That means that we have to turn to talk to Earth every time we need to talk to Earth. Now, the antenna was originally designed to talk to Earth because the Spitzer mission was only designed to last 2.5 to 5 years. And in the end, it lasted 15. So the antenna was designed to only talk to Earth when it was much closer. So all of these things together means there was a natural end of the mission. So this is a coordinate system where the Earth and the Sun are stationary. So this is Spitzer slowly trailing away. So here's, Spitzer leaving Earth, right? So this was the minimum required cryogenic lifetime, right? Actually, that was here, 2.5 years. It lasted a little bit more than 5 years. Cryogen ran out here. After 10 years, it was here. Look at this. It was more than an AU is the distance between the Earth and the Sun. So at its 10-year anniversary is 1.25 AU away. Beyond 1.5 AU, it's still going, right? That was in 2016. It was still going out here at 2020, which is when we turned it off. But look at this. When it was here, it was much closer. It was much easier to talk to Earth. And the solar panels were still in contact with the sun. By the time it's out here, it has to turn to put its antenna to talk to Earth. But look, the sun is starting to impinge on that antenna when it's talking to Earth. So that's a problem, because then you end up warming up your spacecraft every time you talk to Earth. And it makes it harder to charge the batteries if the solar panels are not facing the sun. So that was a challenge, and it resulted in kind of a natural end to the mission. So what kind of orbit does Herschel, and for that matter, JWST, have? Well, those spacecraft orbited around the L2 point. So the Lagrange point, the L2 point, has to do with the gravity in a multi-body system. So here's the sun, here's the Earth and the moon. That's the L2 point. There's L1, L5, L4, 3, but this is L2. So Herschel was out there for a little while. And it turns out there's several satellites in there. So when Herschel was done, they had enough fuel left to kick it out from the L2 point, and that's where JWST is now. Here's another graphic of that. So note that JWST is also away from the Earth-Moon system, so it's also cool. But also note that it's not steadily trailing further and further away from Earth. So the communications are not as challenging. But for all of these infrared missions, cool is absolutely critical. So Spitzer and WISE both carried cryogen on board to help keep them cool. They had Spitzer had a 5.5-year nominal life, and then passive cooling meant that the 2 shortest channels could operate under the warm Spitzer mission until January 2020. For WISE, it had cryogen on board for 10 months, and then could passively cool and operate again only the shortest 2 channels, and it's still operating with those shortest 2 channels. We have learned an awful lot about spacecraft for infrared telescopes since IRAS in 1983. There's tons of really sophisticated engineering and thermodynamics, and these spacecraft manage where the heat and the power and the sunlight go and how to manage it. It's really impressive. So the main takeaway points on orbits is that space is a really harsh place, and where you live affects what kind of and how much science you can do and how long of a life you have. The IR telescopes need to be cool to work. Hubble orbits Earth really close to Earth. Chandra orbits Earth, but in a long elliptical orbit. Spitzer orbits the sun, trailing slowly away from us. Herschel and JWST orbit the sun at Earth's L2 point. And you might remember from one of the other talks, the wavelengths that we're working at. So Spitzer is in there, WISE is in there, Herschel is in there. There's where HST falls. There's where JWST falls. So IRAS, remember, IRAS was the first all-sky infrared mission. IRAS had 62 pixels. Your cell phone camera probably has at least 5 megapixels. This has 62 pixels. I don't mean 62 per wavelength. And it had 4 wavelengths. I mean 62 pixels total. This was few enough pixels that you could know each pixel by name. And the scientists working on it did. So IRAS is really, really good at the big picture of things. It was the first mission to scan the whole sky in the infrared. The instruments that Spitzer had on board, it had 3 instruments. IRAC, the infrared array camera, had 4 channels, 3.6, 4.5, 5.8, and 8 microns in imaging camera. IRS was the infrared spectrograph, which was a low and moderate resolution spectrograph between 5 and 38 microns. MIPS was the multiband imaging photometer for Spitzer. It had a camera that imaged at 2470 and 160 microns. It also actually did really low resolution spectroscopy. IRAC and MIPS 24 had detector arrays with many different pixels that you can effectively think of as more or less like optical CCD. MIPS 70 and MIPS 160 not so much, but they're still arrays of pixels. After Spitzer ran out of cryogen, only the shortest 2 channels of IRAC worked, 3.5 and 4.5 microns. And it was a pointed observatory. It just looked where we pointed it. WISE has 4 channels, 3.5, 4.6, 3.5, 4.5, 12, and 22 microns. Again, there are many pixels for each one of these channels, and you can think of the detectors effectively as CCDs. When the cryogen ran out, it was just the shortest 2 wavelengths that operated, 3.5 and 4.5 microns. And it's a survey telescope, so it scans the whole sky. Herschel had 3 instruments on board. PAX, the photodetector, array camera, and spectrometer. It has imaging at 70, 100, and 160 microns, and spectroscopy between 55 and 200 microns. SPIRE, the spectral and photometric imaging receiver, which has imaging at 250, 350, and 500 microns, and spectroscopy between 200 and 670 microns. And then the spectroscopy instrument is HiFi. You can see now they're giving the band passes in terahertz. That's because the people that are working with that instrument are coming at this from the even longer wavelengths, where they don't think in wavelength, they think in frequency. So they're giving the band pass there in terahertz. If you translate that to microns, it's between 157 and 625 microns. There's no observations after it ran out of cryogen because it really needed the cryogen in order to operate. It was also a pointed observatory, so it only looked where we pointed it. Here's an example of some IRAS data. This was the all sky map. You can see there's 2 black wedges where it didn't quite do the whole sky. In this image, the blue is the 12 micron, the green is the 60 micron, and the red is 100 micron. This is a galactic plane coordinate. So this is the galactic plane here. This is the Large Magellanic Cloud. This blue stuff here is the dust in our solar system. This is in the ecliptic plane. Okay. This is a WISE all-sky map, and they've, I'm pretty sure, subtracted out the ecliptic emission here. So this is just the galactic plane. See the Magellanic Clouds there. You see stuff in the ecliptic plane, or the galactic plane there. Here, blue is 3.5 microns, green is 12, and red is 22 microns. Let's look at just one object for an example. So this is M16, the Eagle Nebula. These are the talons of the eagle. This is a Hubble image. It's the most popular image downloaded from the Hubble website. It's called the Pillars of Creation. It was taken originally with WIFPIC 2. It's an optical image. So this is a relatively tiny footprint. This image is only 1.2 arc minutes on a side, so it's a relatively tiny patch of sky. So this is the same region taken with Spitzer. So in this image, here's that funny footprint from WIFPIC 2, and there's that footprint there. So this image from Spitzer is 4.5, 8, 24, and 70 microns. So the red here is the longest wavelength at 70 microns, and the blue is the 4.5 microns. Okay. This is the IRAS data. I swear to you, it's lined up. It is lined up. Look at those pixels. Those pixels are enormous. That's IRAS data, 12, 25, and 100 microns. How different we have from 1983 to 2004. Huge jumps in technology. It is lined up, I swear to you. That's IRAS. How far we've come between IRAS and Spitzer. All right. Now, here's Spitzer. Let's go to Herschel. Again, it's lined up. Here, the shortest wavelength is 4.5 microns, and longest wavelength is 70, is red. Here, the longest wavelength is 250 microns, that's red. The shortest wavelength is 70. Here, the longest wavelength is 70. Here, the shortest wavelength is 70. How different it is. Here, all those blue dots are stars. So few point sources. The only point sources here are the baby stars that are embedded in the dust. Almost all of this is just dust. Here we're seeing dust and stars. Here it's just dust. The dust we're seeing here is between 10 and 40 Kelvin. Now, WISE data. Again, it's lined up, but look, the WISE data is fuzzy, especially compared to Spitzer. The WISE data is noticeably fuzzy. That's because, even though the WISE wavelengths are comparable to Spitzer's wavelengths, at least at the short end, the WISE telescope is much smaller. So it's much lower resolution. However, the Spitzer data ends. There's no data beyond the edges of this map, really, for Spitzer. But there isn't an end to the WISE data. It just keeps going and going and going and going and going because WISE did the whole sky. So that's the advantage. It's lower spatial resolution, but it covers the whole sky. Pointed observatories like Spitzer and Herschel can't do the whole sky, but they have higher spatial resolution. Stuff like WISE and IRAS do the whole sky, but they have lower spatial resolution. So those kinds of all-sky missions guide the way for follow-up pointed observations like Spitzer or Herschel, or for that matter, JWST. And these issues of resolution and sensitivity really, really, really matter. So one of the things that you can do is the same thing that I just did with the Eagle Nebula. You can find the same object from many different missions. Look at the pixel size, look at the detailed structure, look at the faintest things you can see across different wavelengths, across different missions, across different images. WISE has a very different spatial resolution than Spitzer, or for that matter, 2MASS. Spitzer 24 microns is much worse spatial resolution compared to Spitzer 3.5 or 4.5 micron. Spitzer is way more sensitive than WISE. Here's some examples, some science examples. These are this is a zoom in on a particular couple of galaxies from the Goods field. That galaxy right there is seen in Chandra. It's not seen in Hubble, but it is seen in Spitzer. And this has to do with the astrophysics, because there's enough dust that the optical light isn't getting through. But the X-rays punch through the dust, and Spitzer can see through the dust. So there's astrophysics as well as resolution and sensitivity issues. But look, you can also see the pixels here. Can't see the pixels. Here you can see all sorts of interesting galaxy shapes, whereas for Spitzer, they're just kind of all blobs of the same shape. That's the trade-off. So when I'm talking about artifacts, this is the kind of thing I'm talking about, and resolution. You know intuitively that this picture of this high school game, these are just bright lights. You don't really think that they're big purple wings with streaks coming off. It's just the way that the telescope responded to the bright lights. That's artifacts. So when you start playing around with the real data, and you start worrying about sensitivity and resolution, you also have to worry about artifacts like that. Here's another example of resolution issues. This is a real life example of something that had the right colors to indicate star formation. So I thought it might be a young star with a disk. Here's the WISE images, and it looks like it's a point source. But you go and look in the optical, and it's very clearly not a point source. It turns out to be a galaxy. So I found star formation. I just didn't find star formation in our galaxy. I found star formation in another galaxy. So last one slide about data. All of the missions that I talked about here have ready-to-use data right now. So for both Spitzer and Herschel, the pointed missions don't cover the whole sky, but both of them have data products that are created by the instrument teams, and both of them also have these large science-based teams that are focused on particular subsets of the data. Sometimes they're called legacy teams or heritage teams. They have similar kinds of names. And all of these groups have submitted data back to the archives to be served. So you can grab data that are ready to use from those right now. IRAS and WISE, and for that matter, ACARI, are survey missions. And so they do cover the whole sky. And they have data products that are provided by the mission. You do need to pay attention to the data products because there are often multiple generations of the data products. And depending on exactly what you're doing, you may need to have a different generation of the data products depending on exactly what you need. And so you need to pay attention to exactly what you're doing and exactly which data product you're grabbing in order to do the right science. Grab the right data so you can do good science.